Hi. In the previous module, we talked about how by placing a subject in an MR scanner, we could create a signal. In this module, we'll discuss how we can use this signal to create an image. So recall, when we place the subject into an MR scanner, this causes the nuclei of hydrogen 1 atoms to align with the magnetic field. Now, the hydrogen atoms process about the field at similar frequencies, the Larmor frequency, but at random phase with respect to each other. So each nuclei is a spinning top, and they're spinning out of phase with each other. There is a net longitudinal magnetization in the direction of the field. So next we choose a slice of the brain and use a radio frequency pulse to align the phase, so make them all kind of spin in phase with one another, and also to tip over the nuclei. This causes the longitudinal magnetization to decrease and establishes a transversal magnetization in the XY plane. After the RF pulse is removed, everything seeks to return to equilibrium. And this means that the transverse magnetization is going to disappear in a process known as transversal relaxation, and the longitudinal magnetization grows back to its original size, longitudinal relaxation. So this means that the magnetization is going to return to, say, the z-axis and disappear in the xy plane. Longitudinal relaxation is described by a time constant t1, while transverse relaxation is described by a time constant t2. And during this process, a signal is created that can be measured using a receiver coil, and this is the basic signal that we use in MR. Now, this signal is dependent on T1 and T2 of the different tissue types that we're imaging. Before we go on to how we construct images, it's important to note that most structural MRI and functional MRI scans involve the construction of three-dimensional images based on the use of a series of two-dimensional slices. So we collect slice after slice after slice after slice, and then we combine them to create the three-dimensional volume. Let's concentrate on a single slice of the brain, and let's imagine this brain slice split into a number of equally sized volume elements or voxels. So in the example here, we have this little purple brain, and it's split into 16 different boxes or voxels. Now, the value rho xy corresponds to the signal at point xy, and this could, say, for sake of argument, be the proton density in that area of the brain. Now, when creating an image, we want to compute an intensity for each of these voxels. So in total, we're going to have 16 different intensities, and we're going to get an image that looks something like this. So the darker regions in this image will correspond to areas where there's a lot of protons, and the white ones are areas where there are very few protons. So this gray map image gives us kind of an indication of what the true image looks like, an approximation. Now, how do we use the measured MR signal to make these images? Well, the measured signal combines the information from the entire brain. So basically, you can consider this as the integral over rho over the entire brain in the x and y direction. So it's the combined signal over the entire brain. So that alone is not enough to make an image. So what happens next is we use something called the magnetic field gradient, and that's used to sequentially control the spatial inhomogeneity of the magnetic field so that each measurement can be expressed as follows. So basically what we do here is we put a weight on a spatially dependent weight on each rho value, which depends on its spatial location x and y, but also on two other parameters, kx and ky, which we can control. So what we get here is we get a measurement s kx ky, which is a weighted sum over the proton density, so to speak. Now, these measurements are acquired in the frequency domain. So if you go back and look at that equation that we had here, if you have any background in Fourier analysis, you'll note that this is the Fourier transform. And so the measurements are acquired in the frequency domain, or k-space. And by making measurements for multiple values of kx and ky, we can ultimately gain enough information to solve the inverse problem and get a reconstruction of rho xy at the voxels of interest. And the way we solve this is using the inverse Fourier transform. In practice, of course, data is measured discretely over a finite region, so we have to use discrete Fourier transformations. And so the number of k-space measurements that we need to make is going to ultimately influence the spatial resolution of the image, so how much detail we can make out. So at the end of the day, we need enough measurements to be able to solve the inverse problem. In the example I had where we had 16 different voxels, we need to have enough information to figure out the values of these 16 different voxels. And the way we do that is make 16 different k-space measurements. So we change the values of kx and ky 16 times. And in that case, we have 16 equations, so 16 values of s, kx, ky, and 16 values of rho that we want to solve for. And that's a problem that we can solve. If, for example, we just wanted a 2 by 2 image, such as the one to the right here, we only have 4 unknowns, and then we only need to make 4 k-space measurements. Now, k-space can be sampled in a variety of ways, and we often plot it in a manner like this, that we have kx on one axis and ky on the other, and we talk about changing the values of kx and ky as like transversing through k-space, so moving through k-space. And there's a variety of ways of doing this. On the left, we see what's called echoplanar imaging, so EPI imaging. In this case, we kind of move in a grid-like fashion through kx and ky. And to the right, we see spiral imaging, which you move from the center outward in a spiral. And so both of those are commonly used ways of moving through k-space and sampling data. If you study the Fourier transform, you'll see that the measured k-space data is going to be complex valued. Now, we typically work with what we call magnitude images, and we can obtain these magnitude images by computing the square of the real part of the k-space measurement at a certain voxel plus the square of the imaginary part, and we sum those up and take the square root, and that will give us the magnitude value at that particular voxel. So here's kind of an illustration of what's going on. So we sample data in k-space. In this case, I'm illustrating this using an EPI type trajectory where we sample grid-wise. Once we have enough measurements, we take the inverse Fourier transform and then take the magnitude of all the values of the inverse Fourier transform, and then we get this image, this beautiful brain image here. So again, this kind of illustrates an important fact that the brains aren't measured directly. Instead, you measure the Fourier transform of the brain. So the raw measurements you get from an MR scanner looks like the image to the left here. So it kind of looks like you've dropped a bunch of salt or something on a black table. But if you look at this in 3 dimensions, it's kind of a mountain where there's a big peak in the center and it goes down as we move away. Okay, so that's the end of this module. Here we talked about how we could take a signal acquired from the MR scanner and create an image. In the next module, we're going to talk a little bit more about the concept of k-space. Okay, I'll see you then.